The topic for today is 8051 LCD interfacing programming in assembly and C language. LCD display are dot matrix displays where display elements in the form of dots are arranged in rows and columns. Commonly 5 by 7 and 7 by 9 matrix are used. The displays are available in 16 by 2 or 20 by 2 or 20 by 4 lines. Any character can be formed by switching some dots on and some dots off. It has advantages over the 7 segment LED display. In today's video, I will discuss the LCD display format, LCD interfacing with 8051, the pin description, then the commands, codes, timing for read and write operation, and programming in assembly language and C language. So this video will be longer because we are going to cover the programming in 8051 assembly language as well as the programming in C language. So let us start. Welcome to our channel Engineering and Technology for You. If you are not subscribed to our channel, kindly subscribe and press the bell icon so that you will get notifications for our future videos. The topic for today is 8051 LCD interfacing programming in assembly and C language. Let us start with the introduction. LCD or liquid crystal display is commonly used display apart from 7 segment LED display. There are certain advantages of LCD over the 7 segment displays. Okay. Firstly, the CPU or 8051 has to refresh LEDs continuously to keep displaying the data. So when we are using the multiplexed mode of the 7 segment display, at that time the refreshing of LEDs has to be done continuously by the processor or the CPU. Whereas in LCD, the refreshing controller is present inside the LCD and the CPU or 8051 did not refresh the display. There is no need of refreshing the. Then secondly, the programmer has to send 7 segment codes to the port to display on the 7 segment display. Whereas in LCD, for character including numbers, we can just send the ASCII data. Hence comparatively it is easy to program a LCD for character and graphics. And with the help of this ASCII codes, we can display text as well as numbers. Whereas in 7 segment display, many of the alphabets we can't display. It is very difficult. So the display of long messages is not possible with the help of the 7 segment display. Then lastly, the prices for LCD are coming down over years. So that's why they are readily available and cheap. So we can take advantage of that and make use of the LCD display. So in most of the student based projects, it is advantageous to use the LCD display, as the LCD displays are available at a low cost and we have say 16 characters and 2 lines. So total 32 characters can be displayed. So the display becomes very comfortable. Then even the graphics displays in LCD are also available. Then let us start with the LCD display format. LCD displays are dot matrix displays where display elements in the form of dots are arranged in rows and columns. So typically we have 5 by 7 or 7 by 9 matrix. So these displays 5 by 7 or 7 by 9, it is a matrix display, and by switching the dots on and off from the matrix, we can form any character. So that's why the LCDs are popular because of that. Even we can have some graphics characters and text, the numbers, and even the pictograms. Now there is a read-only memory in the LCD which stores the required dot matrix code for corresponding ASCII input. So here we have to give the ASCII value as the input to the LCD, and then as per the ASCII value it will display the particular character. For example, the ASCII value for A, that is capital A, it is 41H. So if you give 41, it will display A. So using the dot matrix text, we can display the text, then pictograms, graphics, and even the numbers. So the commercially available LCD displays, they are Hitachi 44780 and Optrex DMC 16XX, DMC 16XXX. These are the two series. Then similarly we have the DMC 20 character series and DMC 24 character series. So in this way, these are the formats for the LCD display. Then let us take an overview of the LCD interfacing. So if you look at this figure, now here we'll have to connect the different pins of LCD to the controller. Now in this case I have shown 8051 microcontroller because that is what we are going to study today. Now the pins, it has got 8 pins for the data lines D0 to D7, and there is a pin for register select, that is for data and command. These two registers are present in LCD. So for selecting that, we'll have to send either 0 or 1 on this. Then for reading and writing operation, we have the RW, and for enabling we have the E pin, so that will enable the data latch. So when RS is equal to 0, it is for the command rest, and RS is equal to 1, it is for the data rest. And similarly, RW is equal to 0, it is for the write operation, and RW is equal to 1, it is for the read operation. And for enabling, we have to make this E pin high to low. So high to low transition will latch the data present on the data lines. So the data lines are D0 to D7, they are bidirectional data or command pins. So both the commands and data, they are transferred by these lines. Then the alphanumeric characters, they are sent in the ASCII format. So if you look at this figure here, these four, this E, RW and RS, these three pins, they are connected to particular port pin of 8051, and the 8 lines, there is DB0 to DB7 or D0 to D7, they are connected to one port of 8051. And here we are just shown the LCD module. It will be seen in this way, and this is the communication bus which will, this is the controller which will communicate with the LCD module for the display. So now when we are interfacing, we'll have to see that we make the connections properly, and then with the help of the command register and data register, we must send the command and the data properly with the help of timing. And every time when we send the data, we have to enable with the help of this E pin. So these are the things which are taken care when we are interfacing. Then steps to display data on LCD. The first step is to initialize the LCD with a set of command words. So these command words will be sent on the data lines D0 to D7 with RS is equal to 0, because RS is equal to 0 means it will be for the command, and RW is equal to 0, that is the write operation. So when we are sending the command words, they are to be written on the LCD, and the E pin has to go from high to low, so that will latch the commands. Then the second step is sending the data. So the ASCII value of the character to be displayed. Say for example, if you want to display A, the ASCII code for A is 41 hexadecimal, 41H. So it is sent on the data lines D0 to D7. Now here, when we are sending the ASCII code, at that time this RS should be 1, because that is for the data register select, that should be 1. Then RW, again it should be 0 if you want to write it, and high to low pulse on E. So these three things we have to take care every time. Then the LCD commands. The LCD controller can accept several commands and modify the display accordingly. So generally these commands are given to set or initialize the display and set the display for particular display mode. So these commands will say clear the screen, return home, increment or decrement cursor, that is the position of the cursor is incremented or decremented, because generally the display will be 16 by 2 lines or 16 by 1 line, 20 by 1 line, like that. So that's why we have to position the display accordingly. So for that, different commands are there. We are going to see the details. So after writing to the LCD, it takes some time for it to complete its internal operations. So during this time, it will not accept any new command or data. We will have to wait. So that's why in the program we'll have to insert time delay between any two commands or data sent to the. So again, this we are going to see when we actually see the program. Now the pin description. So this is a LCD displays 16 by 2. There are 14 pin. So Pin number 1 is ground, and this is VCC plus 5V supply, and third pin is VE, that is for this is the power supply to control the contrast or the display brightness, you can see. Then RS, now this is a input pin, so RS is equal to 0 to select command register, and RS is equal to 1 to select the data register. Then RW, again it is a input pin, so RW is equal to 0 for write, and RW is equal to 1 for read operation. Then E is enable, so this pin has to, in order to enable the latch, you have to make a transition from high to low. So first we'll make it high, and then after certain small delay we'll make it low. Then DB0 to DB7, they are nothing but the 8-bit data bus, so they are from pin 7 to 14. These are the 8 lines. Then command codes. Now here the LCD register, instruction register, will have these commands, so the code is in hexadecimal. Say for example here 01, it is for the clear display screen. So when we want to clear the display screen, we give the command 01 or send hexadecimal code 01 to the LCD. Then 2 is for return home. Then 04 is for decrement cursor, that is shift cursor to the left. Then 6 is for increment cursor, that is shift cursor to the right. Then similarly 5 shift display right, shift display left. So here we can position the display also. Then 0A, that is for making the display off, cursor on. Then display on, cursor off, that is 0C. Then 0E is display on, cursor on. So while programming, we'll have to make use of these commands. So if you want to make the display on as well as the cursor on, so then we can use 0E, and then 0F, display on, cursor blinking. So when the cursor is blinking, we'll know the position of the cursor. Then 10, that is for shift cursor position to the left. Then 14 is shift cursor position to the right. Then 18 is shift entire display to the left, shift entire display to the right. So entire display means whatever characters we are displaying, those can be shifted to the left or right with the help of these commands. Then 2 important commands. 80, the code 80 hexadecimal will force cursor to the beginning of the first line. See, if we are using 16:2 display, 16 character by 2 lines, so first line if you want to display, we'll have to make use of 80, and for the second line we'll have to make use of C0. These are hexadecimal codes. Then 38, there is 2 lines and 5x7 matrix. So this is the common display which is used for the most of the projects. So out of all these commands, only few will be used. Say 38, 80, C0, then this display on, cursor on, 0, say 0E, then some of the commands here 6, then 1, only few will be used. So when we write the program, at that time we'll make use of. Then the addressing, LCD addressing. See, we have different types of displays, 16:2, then 20:1, 20:2. So 16 by 2 LCD means it is having 16 characters in 2 lines. So uh, first line will have the code for the starting code will be 80, then next will be 81, 82, like that will be up to 8F. Similarly, the second line will have the code C0, C1, C2, C3 and so on up to CF. Then if you take another display 20 by 2, it will have these codes. Only here this side it will go up to 93, this will go up to D3. Then 20 by 4, this will have 4 lines. Then 40 by 2 will go up to A7. So that's why in this table we have shown the cursor addresses for some of the displays, and here general the minimum it will be 1000, that is 8 0 0 0 0 80, and maximum will be 1010 A and 01117. So that is the last A7, and line 2 will start from C0, it is 1100 and 0000, that is C0, and last maximum will be E7, that is 1110 and 0111. So that is how the address for the particular position in the display is given here. Let us see the timing diagram for read operation. Now here the read requires a low to high pulse for E pin. So the enable pin, it will go from say low to high, and then it has to remain high for a certain time for the read operation. So this is the data output delay time, so TD, and the data will be present here after this time on this data lines D0 to D7. Now for the read operation R/W, this signal has to go high. So there is a signal TAS, that is setup time prior to E, for both RS and RW, that is 140 nanoseconds, and there is another time TAH, that is the whole time after E has come down from both RS and RW, so that is 10 nanoseconds. So for both these the same time is there, so that's why the read operation has to be carried out during this period when E is high and the data is available on the data bus D0 to, and for read operation this RW signal, it has to be high. So RS, this it will be low for the particular command register, it is low for the command register, then only we can read the signal. Then we have the timing diagram for the write signal. So for write, again when we are writing the data to the LCD, at that time we'll have to make use of this. So again the E signal will enable the data, and then this TAS, that is the 140 nanosecond minimum time, this setup time prior to E going high, and this time is the enable pulse width TPWH, so that is 450 nanoseconds, and again this is 10 nanoseconds as we have seen earlier also. So the writing has to be performed during this period when E is high. So this DSW, so this is the data setup time, that is 195 nanoseconds. So during this time only the data can be written onto the LCD. So data is available on the data bus and the enable signal is high, and here the read write signal, so it will go low for the write operation, and the RS, it will go low for the command. So when we are writing the command, at that time this will be low, this will also be low. Like this we have to follow. So in the programming we'll just provide the delay regularly for that. Now let us see the interfacing diagram with the 8051. So when we are to interface the data lines D0 to D7, they are connected to port 1 of 8051. So P1.0 to P1.7, these lines. D0 will be connected to P1.0, P1 will be connected to P1.1, and so on. So these are the 8 lines, and the register select, that is connected to port 2.0 pin. So it's a register select input pin. Then RW, again it is a input pin, it will be connected to P2.1, and enable pin is connected to P2.2. So these are the 3 pins which are connected to 8051, and these are 8 pins again connected to port 1. 3 pins are connected to port 2. And here we have the connections for the VCC, that is plus 5 volt, and this is a 10K potentiometer through which we are connecting it to the VE, so for controlling the LCD light intensity, contrast of the LCD. And this is the ground pin, which is grounded. So the connection is very simple. Now let us go for the programming. So here we'll take an example. Write program to display hello on the LCD display. So we'll be displaying 5 alphabets HELLO on the display. So the algorithm for this is initialize the LCD using the INIT LCD subroutine. We will be writing a subroutine INIT LCD for initializing the LCD. Then second step is to send the ASCII value H to port 1 and call the data write subroutine. So here we'll send the ASCII value H to port 1 of 8051, and then we'll call the data write signal at data write subroutine, so that whatever the ASCII value of H, it will be written onto the LCD. And these steps 2 is repeated for other characters ELLO, and once we complete that, the will be in the loop. You have to wait. So this is simple algorithm for displaying the display HELLO hello. So first let us see the INIT LCD subroutine, that is for initializing the LCD. So first part here, send the command 38 to port 1. So we have to first specify the display type. So 38 we have seen, it is for the say 2-line display 5/7, 16/2, 5/7 matrix. So and call the command write. So command write subroutine, it will always write the command to the LCD. So here we'll send the command to port 1 and then call the command write subroutine. So the first command, the code for first command, that is 38, will go to the LCD. Then repeat step 1 for commands 0E0180. We are just using these commands. 38, it is for 2 lines 5x7 matrix. Then 0 is for display on, cursor on. 01 is for clear display, and 80 is for cursor position 0 on line 1. So these 4 commands will be using. So we'll have to send the command to port 1 and then call command write subroutine. So that will be common for all these commands. Then command write subroutine. So in the command write subroutine, we have to write the command to the command register. So that's why we'll have to make RS, that is pin number 2.0, and RW. So these 2 pins, they have to be low, they are 0 for the command and write. So RS is equal to 0 means it will select the command register, and RW is equal to 0 means it will select the write operation. Then make enable pin E, so that is connected to port 2.2 of 8051. We'll have to make it high for 1 millisecond. Then make it low. So this 1 millisecond, that is the time when the pin will remain high and the writing of the command will be completed during this 1 millisecond, as we have seen the timing diagram, as per the timing diagram. Then once we make the pin low, so the transition from high to low, so that will occur and the command will be latched in the LCD. Then we call a delay of 250 milliseconds because the LCD will not accept any command immediately. We have to call a delay of 250 milliseconds. Then return to calling program. So this is subroutine, so it will go back to the main program. Then next is data write subroutine. So in the data write subroutine, we'll have to make RS is equal to 1. So that is for data register. For command, RS was equal to 0. So for data it is 1. And RW is equal to 0 for the write operation, because here we are writing the data, that is the ASCII value. Then make E is equal to 1 for 1 milliseconds, that is the common, and make E is equal to 0, that is we'll have to make it high and then low. Then we have to call the delay of 250 milliseconds, that is once this operation is done, then the LCD will not do anything, so we'll have to call the delay of 250 milliseconds, and then again we have to return to the main program. So that will be the function of the data write subroutine. It will write the data in the LCD, in the data register of the. So let us see how we can write a program in the assembly language. So this is the assembly language program for LCD interfacing. So already we have seen some of the assembler directives. org, that is for the start of the program. So first we make the vector 0 and then jump to start, where we are making the starting point at 30H, just to avoid the first few locations in memory. We are going to the scratchpad RAM. That location is 30. Starting location is 30. So here these assembler directives, I have made another video on that. Is on my YouTube channel. You can watch it if you are interested. So here we are starting. So in the start we are calling the INIT LCD, that is initialize LCD subroutine. So when we call the INIT LCD subroutine, the initialization of the LCD will be done. Then we take the first character to be displayed, that is the ASCII value of the first character, that is ASCII value of H, and put it in accumulator. So move A comma hash H. So here we are using the immediate addressing and moving the ASCII value of H into the accumulator. Then after this we call the data write subroutine. So this subroutine will put the data into the LCD, and so that's why it will be used for displaying on the LCD. The initialized LCD will position the character as per the commands, and then when we call the data write, it will display the data on the LCD. Then same thing we do for the character E. So we load it into the accumulator, move A comma hash E. ASCII value of E is loaded into the accumulator. Then again we call the data write, so that will be displaying the character E. Then next we load the character L into the accumulator, and again we call the data write subroutine, so that will display character L. Then again we load another L into the accumulator, and again call the data write subroutine, so that will display this L. And lastly we load the ASCII value of O in accumulator, and again call the data write subroutine, so that will display the O character. And then we are here in the loop, so we'll be waiting in the loop. So this is the main program for the LCD interfacing. Now it's not very hard, just we have to call the subroutine for initializing the LCD, and then load the ASCII value of H, E, L, L, O into the accumulator, and call the data write subroutine. That is what we do in this main program. Then the data write subroutine. Now in the data write subroutine, whatever we have loaded the ASCII value, the character to be displayed in accumulator, so that will be sent to the port 1. So send data on port 1. So port 1 we have connected the data lines D0 to D7. Then for port 2, now what we'll do, now this is the data, so we'll have to make RS1. So port 2.0, that is connected to RS, so we'll set the bit P2.0. and this RW should be 0 for the write operation. So we'll clear P2.1. because RW is connected to P2.1. Then enable. Now enable will have to first make it high. It is connected to port 2.2. So we'll set bit P2.2. So enable pin will be high. Then we'll call small delay, that is for the 1 milliseconds delay, and then we clear the enable pin, we make it low. So clear P2.2 will clear enable pin, it will make it 0. So enable pin we have made it high and then low. So during this period the data will be returned into the LCD. After that we call call delay. So that is a large delay or high amount of delay we have given in for this, and then we return. So this is what is done in the data write subroutine. Then the command write subroutine. So when we are writing the command, so first whatever command we have loaded into the accumulator, that will be loaded into port 1 of 8051. Then for the command RS should be 0. So we'll clear P2.0 and clear 2.1, that is for writing operation, will clear it, and enable will make it high, set P2.2. So in E will be high here. Then we call a small delay, that is 1 millisecond delay, and then we make the E low. So clear P2.2 will clear the enable pin. Then again we call a high delay, that is 250 milliseconds, because the LCD will not respond immediately after the data has been written, command has been written. So after this delay will return back to the main program. So this is how the command write subroutine will be used to write commands to the LCD. Then the initialize LCD subroutine, INIT LCD. So first of all we load A with 38. This hexadecimal code which will define that the display is 2 lines and 5x7 matrix. So once we display this, load this into the accumulator, then we call the command write. So the command write subroutine will write this command, that is 38H, into the LCD. So the LCD will be set as 2 lines 5x7 matrix. Then we load A with 0E command code. So this is command code for display on and cursor on. So it will make the LCD display on and the cursor will also be on when we call command write. Then after this we call load the accumulator with 01, that is for the clearing the display, LCD display. So when we load accumulator with 01, then we again call the command write. So the command write subroutine will write the command onto the LCD. The RS will be 0 and RW will be again 0 for the writing the command. Then next we write the we load the command 06, that is for shift cursor right. So when we are displaying the character, at that time we'll have to shift the next character to the right. So H, then L, H E, then L L O, like that. So that's why you have to shift the cursor right by one position. So for that we have the command 06 hexadecimal. So when we call the command right, the cursor will be shifted right by one position. Then here the command we are giving is display on line 1. So this is for 80. So when we are displaying, we are starting from the line 1 and the address we are using is 80. This position 1 on line 1. So when we give this command, this 80 will be the command given to the LCD. So the display will start on line 1 at position 1. So this is the initialization subroutine for the LCD. So the last is the return from this subroutine. Then the delay subroutine, that is the high delay. So here we are loading the register R3 with value 250 and R4 with the value 255. Then this is the loop DJ and Z R4 loop 2. So it will be in this loop until it becomes 0. Then again it will decrement R3 and then this will be in this loop. So we'll get a total delay of 250 milliseconds with the help of this subroutine. Then delay 1 subroutine. Now this is for the small delay. So that's why we have changed the value of R3 to 10. So approximately it will give us 1 milliseconds delay. So in this way, same routine is there. Then let us see the last part, that is the C program for LCD interfacing 8051. When we now the same thing we are trying to do here, that is displaying the characters HELLO on the display. So and our programming will be also similar to what we have done in assembly language, only here we'll be using the syntax of C language. So first of all, we'll have to include the reg51.h header file, because this header file will have all the functions related to the registers of 8051. So it is necessary to include this when we are programming in. Then first we write the main function void main. So this is the init LCD function, initialize LCD, similar to initialize LCD subroutine. Here we have the function, instead of subroutine we have the function. Then we have the LCD data function for displaying H, LCD data with E passed to that is for displaying E. And similarly LCD data L, LCD data L and LCD data O, that is for displaying the particular character. And here we will be in the loop while 1. So while this is true, this will be continued. So we come to the end of the main program here. Then let us go to the function LCD data. So this LCD data we are passing the unsigned character value here. So first we are passing h, whatever is the value we are passing, so the value will be going to port 1. So output data on D0 to D7 at port P1. Then port 2.0 will have to make it 1. So for data RS has to be 1. Then RW has to be 0 for the write operation. So we'll make this pin 2.10. Then pin 2.2, that is for the enable. So we'll make it high, that is equal to 1 for enable high to low. So this pulse is high to low enable pulse. Then we call delay 1, that is the small delay. And again we make this P 2.2 low, that is enable, we are making it 0. And now we call the large delay, that is delay we are passing 250 here we are passing only 1. Then return, then we'll return to the main function. Then let us go to the LCD command. Now this is similar to the command write. So I'll say the name of the function is LCD command CMD, VLCD CMD. So here we'll be passing unsigned character command. Instead of data we are passing command here. Then whatever we pass to this function, so that will be assigned to port 1. So output command on D0 to D7 at port P1. Then RS is equal to 0 for command. So we'll make this P 2.0 is equal to 0. Then P 2.1, that is made 0 for the write operation. And P 2.2, that is enable signal, we are making it high. So high to low transition. Then we'll give a delay of 1 milliseconds and then make it low. So P 2.2 is equal to 0. That will make the enable pin. Then we give a large delay, to delay 250. So we are passing this parameter 250. It will produce a delay of 250 milliseconds. Earlier it was just 1 millisecond, here it is 250. And then we return to the main function, main program. Then function INIT LCD. So this is similar to the INIT LCD subroutine. So again here we are not passing anything to this. So LCD CMD, this is the hexadecimal value 38. So that will define 2 lines 5x7 matrix. Then LCD CMD 0E, that is cursor on display, then LCD on. Then LCD CMD 01, that will clear the LCD display. Then LCD CMD 06, that is for shift right. So one by one it will display the characters. H, then one position shifted, E, then L, then L, and O, like that. Then LCD CMD 80, that is the first character will be written on the first line the display. That's why this address is 80. Then we return. Then coming to the delay function. Now this delay function, we are going to pass a unsigned integer value initial to this delay function. So as per the value of this initial, we can change the delay timing. Here, when we are passing out this initial, will be assigned to integer. Say this initial is coming from the main, and when we are writing the for loops here, we are first we are defining two unsigned integers I and j, and then we are writing the for loop for I. So this will go up to, say, I is equal to 0, I less than initial. So whatever parameter we are passing here as initial, so this loop will be executed number of times according to this. That's why the delay will be multiplied by this number. So when we need a large bit delay, at that time we can pass this value 250 to the initial. So this delay, now the second delay which is generated by j for loop. So for j is equal to 0, j less than 1275, j plus plus. So this for loop is going to give us delay of 1 millisecond. And when we want a delay of 250 milliseconds, then we are using this loop here, and the parameter 250 is passed to the initial we can say the initial variable. So the delay of 1 millisecond is multiplied by 250, and we get delay of 250 milliseconds. So in this way, there is no need to write two separate delay subroutines as we have written in the assembly language. Here we can just pass the parameters in the C function, and then as per the parameter we can get the delay. So that is the advantage of using the higher level language or HLL. So you can see, compare both the programs. The program written in assembly language, they are longer, whereas the program written in C is quite short. So in this way you can when you are writing the software for your project, at that time you can prefer the C language and write the code using the C language. So now with this we come to the end of this video. If you have any queries regarding this particular video, you can contact me on Facebook, Twitter, Gmail or Instagram. Or even if you have any queries when you are doing your project work, you can contact me and get your queries. Then if you like the video, press the like button, share with your friends with the help of this icon which is available on the YouTube. Directly you can share the video. Then subscribe to our channel Engineering and Technology for more videos on this subject. I will be covering some interfacing part using the PIC and the 805. Then don't forget to press the bell icon to get notifications about our future video. Then thanks for watching. Have a nice day.